Okay, let's start now. Good evening, everyone. Today, we are going to embark on a fascinating journey into the machine learning field. But first, let's understand what machine learning is. So back in 1959, the author, he is a pioneer in the field of artificial intelligence. He defined machine learning as a field of study that gives computers the ability to learn without clearly programmed. In simpler terms, the machine learning allows computer to learn from data and improve their performance without human interventions. He's famous for an interesting checker playing program. And the amazing thing about that is himself was not a very good checker player. And what he did was he let the computer to play the checker many, many times against itself. And by watching what kind of board position tend to win and what kind of board position tend to lead to loses, it can try to achieve a good position and avoid bad position. And the program learned better and better in playing checkers, and finally become a better checker player than author himself. Okay, so let's start with a type of machine learning called supervised learning. In supervised learning, the machine can learn from the label data. The label data means we provide the algorithm with input and output pairs, which is X and Y here. So as we can see, there are input data X, and also it has the output label Y here. So there is X and Y respectively. So we can try to find a pattern between the input and output. And when given a new input, we can predict according the pattern that we found. So in one short sentence, the supervised learning is learns from being given right answers. So the concept is maybe is a bit abstract. Let me clarify this concept by a few examples. So first, imagine you want to predict the price of a house based on its size. We will provide the machine with historical data where the sizes of houses and their respective prices are known. And using this data, the machine will learn the relationship between the house size and the price. So as we can see in this graph, the X is the house size and the Y is the price. Uh, so each of the point is the data point, and they together form the data set. So as we can see, since the input of X has its label Y, so it is supervised learning because it has a label. And another example would be predicting university admissions. So let's say we want to predict if a student will be admitted or not to a university based on the exam scores. And by training our model on historical data of students and their admission status, our machine can make predictions for new students. And lastly, consider an email system that classifies emails as spam or not. So the system is trained on emails where we already know it's spam or not. So typically we will label a lot of email and tell the machine whether they're spam or not, and they are training based on this. And finally, it can clarify new emails automatically in the future. Mm, so that is the supervised learning. And for unsupervised learning, uh, here the machine learns from unlabeled data. The goal is not to predict a specific output, but to discover patterns or structures within the data. So, for example, imagine a company uh, who is trying to segment the customers based on their purchasing behavior. So we don't know in advance what these segments or groups might be. So unsupervised learning would help the company to find these customer groups without any period definitions. So as we can see here, there are monetary, frequency, and recency, which are the different inputs of the model. And actually, we didn't give its output. So the machine will learn by itself to clustering or grouping the data. As we can see, there are different colors that belongs to different groups, which is made by the machine himself. So in one short sentence, the grouping without giving any label or right answers is the unsupervised learning. Okay, let's use a simple example to understand the difference between supervised and unsupervised learning. So as we can see here, supervised learning is data with label and try to predict. So the given data here is a cat photo and a dog photo. So for supervised learning, it must have a label that indicates this photo is the cat and this photo is dog. And the task is to predict a new photo, whether it's a cat or dog or something. So when given such a photo, the program will, the output will be cat. So that is supervised learning. The characteristic of supervised learning is that they have the labels. And for non-supervised learning, is given the data with no label and try to group them meaningfully. For example, if the machine is given these three photos, it can automatically groups is into two categories, which is the group one and group two, based on some characteristic of the photos. Okay, so let's get a quick summary of the supervised learning and unsupervised learning. So for definition, in supervised learning, the algorithm must learn from the label training data. And the goal of the supervised learning is to learn mapping from the inputs to outputs and able to make predictions on new unseen data. And there are a lot of algorithms under the supervised learning. Actually, almost 80% of the application is under the supervised learning. So like some common algorithms include linear regression, logistic regression, decision tree, SVM, random forest, and so on. And for unsupervised learning, an algorithm learns from the unlabeled data and finding the hidden structures in the data without giving any label. So the main goals can be to find the cluster within the data, which is the clustering. And one very typical algorithms under the unsupervised learning is the k-means algorithm. And today we are going to focus on these two algorithms under the supervised learning. That's because the linear regression and logistic regression are very important to not only machine learning, but also deep learning, which will be delivered in next week's workshops focused on deep learning. So today we are going to establish foundations of these two components of machine learning. All right, next we'll dive into the topic of linear regression. This topic meaning consists of three parts. Firstly, we need to define our data set, which I personally believe is a very crucial step. This is because understanding the data set isn't always as straightforward as we may think, and it sometimes cause a lot of confusion for beginners. And secondly, we will talk about the linear regression model. And thirdly, we will dive into the details of the loss function. And here, just a reminder that linear regression can be either single variable, which we are familiar like that, or they can also be multivariables, which is indicates like that. So let's start with define the data set. To recap what we just learned about the supervised learning, the linear regression is a supervised learning. So in supervised learning, we have input X and the output label Y. So our data set can be represented as a collection of XY pairs like this. The data set D should equals to X1, Y1, X2, Y2, and all the way to XM, YM. As shown in the illustration on the right, the X represents the horizontal axis and the Y represents the vertical X. But this graph is a very simplified scenario, which the X only has one single number here and Y is also a single number. But in reality, X isn't always just one number. In our example, the X is just the house size, but actually it can be a set rather than just a single number. So We will explain with the following example. We will use a very famous data set in machine learning, which is the Chetnik data set, which contains information on survivors and non-survivors from the Titanic disasters. And from this example, we will try to understand that the input X is not always a single number. So let's analyze this table. The first column is the index ranging from 0, 1, 2, 3, 4, all the way to n. And only a portion of the chart is displayed here. And each row represents a passenger and shows variable pieces of information about them. And the column labeled with survive, which is here, is obviously the output, because that is the result or the outcome of the disaster. So that is the output, which is the label, or we can say Y here. And this is Y1, Y2, all the way to Yn. And each passenger can be seen as an input. As we can see here, this is one in X1 and X2, and they together form the input X. And as we can see here, the input is not just a single number. Actually, it is consists of many attributes, like the passenger name, sex, age, or something like that. They together form one input, and we call it a sample. And all the samples together form the data set X as the whole input. So that is the thing that is very easy to lead to confusion. So X1, all the way to Xm are the samples. They are the samples, and each samples has D attributes, which are the columns. These are the attributes under the samples. And the survive or not is the Y, which is the outcome, or we can say label. Okay, let's define it mathematically. If the capital X represents the entire input, then it should consist M input, which is X1, X2, all the way to Xm. That is the samples. Here in the data set, we have M samples. So the capital X is consisted of X1, X2, all the way to Xm, where we can write like that. Because each sample is consist of D attributes. So for here, each sample is not just a single number. They are actually consist of D contributes. So actually, X is a matrix like that. Each row is samples, and each column is a attribute. So together they form a matrix of the input X. And for Y, it's relatively easy because Y is usually only just a single number. So Y is consists of Y1 all the way to Yn, which is usually only have one single number or category. However, the X1, X2, all the way to Xn can refers to samples in some contexts, but they can also refer to attributes in other contexts, which may cause a lot of confusion. So my advice is each time when you see the structure like X1, X2, all the way to Xm, the first thing to do is to identify whether they are samples or attributes according the context. So next, we will look at the linear regression model. This model predicts the output or the corresponding Y value based on the attributes. So as we can see here, the X1, X2, all the way to XD is the attributes, not the samples. Because we use these attributes to predict the Y value for one sample. So actually, they are attributes, not samples, as we just said. So the fx here represents the predict value, which has difference with Y, which always used to indicate real output. Fx is the predict output, and Y is the real output. Uh, and here the linear regression function is given here. For each sample with D attributes, it can give a predicted value fx according to this function. And the W and B here are the parameter we need to find because the input are given and the predict value are calculated. So what we need to find is all the W and the B. We try to find the best value of the parameter to let our model fit the data set best. So here is a visualization. Mm, for input X, the rows are the data points and the columns are the features. And it can be divided into X1, X2, all the way to XD, which are the features with different weights. And each data point has a corresponding prediction fx vector, which we use this formula to predict the y value, which is the fx. Okay, then let's take a look at the cost function. The problem here is how to find the best value of the parameter. Our aim is to minimize the error between the predicted value and the real value. So the most important thing is to define what is the error in mathematical way. So here, the MSE is the most common indicator to show the model's performance. Mm, uh, so we've tried to find some parameters that allows the MSE of this model has the minimal value. So loss function in this context is refers to MSE, which is the mean square error. So mean square error is the very common loss function used for linear regression. And mathematically, it's defined like that. The W equals to this one. And here is the arc mean, which refers to the, the, the parameter value that can minimize the following expression with it here. And this is the loss function, which is expressed as MSE mean square error. And when in some simple scenario, each sample only has one attribute, then we can write yi in the form of wxi plus b. So this is a simplified formula here. Mm. So argmin used to describe the argument. So yeah, as we just said, and this this two means the optimal value of W and B. Okay. And here is the detailed calculation of the parameter B and W. However, I won't go to very detail of this calculation, but I put it here. So those who are interested, you can take a look. Okay. So the computer, actually how the computer gets the value of the W and B is use Guardian descent method, which is actually shown here. But in computer calculation, is there is some if we can there is a visualization of the calculation process. As we can see here, this is the y is the loss and the x is the value of weight. So actually we start with here, and after iteration, the loss will reduce to its the minimal point. So after after the loss achieving the minimal point, we can get the optimal parameter because the parameter here enable the loss to become the minimal value. So the parameter here is the optimal parameter. So as we can see here, this is the initial line which cannot fit the data set appropriately. But however, after the iterations, it becomes better and better, which finally achieve the best line with the optimal parameters. This process is done by the gradient descent method. And as we can see here, during the training process, the mean square error is reduced all the way. So a quick summary here. A data set is often represented as a matrix, where each row is a different sample and each column is a different attribute. And the linear regression model makes a prediction by computing a weighted sum of the input. And the loss function measures how well the model predicts the y. For linear regression, the most commonly used loss function is the mean square error, which is MSE. This is a loss function, and which is the average of the square difference between the predict value and the actual value. Okay. So far, we have a general understanding of the linear regression. Now, we are going to discuss a regression problem that is very important in deep learning, that is logistic regression. In this section, we will first understand the types of variables, include numeric and categorical variable. And then we will learn what logistic regression is and see some examples and identify the difference between logistic and linear regression. And the key focus will be on the sigmoid function, followed by application of logistic regression. Firstly, it's important to understand the difference between numeric and categorical variable. Numerical variable represents measurable quantities such as age, height, and weight, which have precise mathematical meanings. On the other hand, categorical variable represents distinct groups or categories. They can be denoted by letters like M for male and F for female, or even by numbers like 1 for male and 2 for female. However, even the number are used, remember that it's still a categorical variable because number don't carry any computational value. It's just meaning it's just the labels for categories. So let's again use the technique dataset to practice distinguish between the two types. So the survival, which indicates whether the passenger survived or not, is obviously is a categorical variable. And the P class representing the class of ticket that passenger purchased is also a categorical variable because even though the numbers are used here, the numbers here denotes to different types, so it doesn't contain any mathematical meaning, so it's still a categorical variable. And for the name is the name of the passenger, and embark is the port where the passenger board the Titanic. As we can see here, they are all the categorical value, and sex ticket are also categorical value. And for numeric value, the age and fire, which is considered of number. So and they actually contains the mathematical meanings, so they are numeric. And parse, it means the number of parents or children the passenger had aboard the Titanic. So it's a number of real things. So it's also a numeric variable. So similarly, SIP-SAP, which is the numbers of siblings or supposes the passengers had aboard the Titanic, is also a numeric value. And having this in mind, let's explore the logistic regression. Oh, okay. I missed one variable. The passenger line is a unique number to assign to each passenger in the ticket. However, it's just a random series of number which contains no meaning. So actually is a numeric although it's a numeric value, it's typically treated as a nominal categorical value because it's simply an identifier and does not have any cognitive significance. However, in our analysis, in data analysis, uh, such how to such variable is sometimes we don't use. We just simply don't use such variable in our analysis. Okay, having this in mind, we can explore the logistic regression. And logistic regression is a type of regression analysis used to predict a categorical outcome based on one or more predictors. Typically, the outcome is binary, as illustrated. While regular linear regression estimate a numeric value, logistic regression take it a step further by converting the obtained numeric value through a function, which we call the sigmoid function, and turning it into the categorical outcome. So here, from this step to this step, this is the linear regression. And after that, we apply a sigmoid function to this, and then it then has a categorical outcome, which is the logistic regression. Let's consider an example, predicting if a student get admitted to a university based on their exam scores. Imagine we have data from 100 students, each with scores from 2 exams. And the final admission decision could be represented by 1 admitted and 0 not admitted. This scenario is perfectly suited for our logistic regression model because there are numeric value input and also the categorical value output. So we can slow this performance by logistic regression. And let's compare the logistic regression to linear regression to enhance the understanding. So linear regression is used to predict a numerical outcome. The result is typically a number. And in contrast, logistic regression predicts the likelihood of a sample belonging to a particular category. And the final result is the probability of which category the input belongs to. And earlier, we mentioned the sigmoid function in transitioning from linear to logistic regression. And this function converts the output of traditional linear regression into a probability, making it suitable for logistic regression. And the function is defined as 1 over 1 plus raised to the negative power of x, which is here. And the function can accept any value from negative infinity to positive infinity. So that we can ensure that any numeric inputs can get its transformation into a value between 0 and 1. And the outcome between 0 and 1, this indicates the probability of a particular category. And usually, if the probability that it belongs to the positive category is higher than 0.5, then we categorize it as a positive category. And if it is lower than 0.5, then we classify it as negative. Okay, there are some sorry. There are some characteristics of the sigmoid function. First is a S-shaped curve. The sigmoid function produce an S-shaped curve, which we call a sigmoid curve. And the output range is from 0 to 1. So which make it useful for interpreting the output as a probability. And it's centered at 0.5. When the input is 0.5, and when the input is 0.5, the output is also 0.5. Oh, sorry. When the input is 0, then the output is 0.5. And when input is larger than 0, then is higher than 0.5. When input is lower than 0.5, when input is lower than 0, then the output is lower than 0.5. and when it approach the infinity, the output will also approach the 0 and 1 respectively. And here is the loss function that we usually use for classification tests. We have used MSE for linear regression cost function. However, here, because the outcome is categorical, so we cannot apply MSE calculation to the predict y and the real y. So actually, we are using binary cross entropy, which is shown here. However, this formula is quite complex, and actually, we do not need to understand it too deeply. So we can just look at these two graphs. For the label y equals to 1, if we predict y as 0, then it will have a high cost. And if we predict it as 1, then it's the same as the answer, then the loss is 0. And similarly, if label y equals to 0 and we predict it as 0, then there is no cost. And we predict it as 1, then it will have a high cost. So by using the mathematical method, we can reduce the cost function to the minimal. And by doing so, we can find the optimal set of the parameter, just very similar to the what we did to MSE. Okay, and this is the training process of the machine learning. First, we have the X, capital X, which is the input of the model, and the model when we get input, it will produce the output fx, which is the prediction, and it can have some difference with the label y, and by comparing the fx and y, we can acquire the loss function. The loss function is to measure the difference between fx and y. And by reduce the loss function to the minimal point, we can acquire the optimal set of parameter. Okay, and this is an application of the logistic regression. In the deep learning area, the basic unit is the perceptron, which is shown here. As we can see, there are many inputs, and they are multiplied with the weight and sum up. And this part is the linear regression part. And after that, we use a sigmoid function to it. And then the whole part is the logistic regression. So as we can see here, the logistic regression has each application in the unit of neural network, which is the foundation of deep learning. Okay, so that's the end of my part. Let's have a break. And after that, I will deliver some code implementation for you. Thank you.
So thank you, Tianhe. So that was Tianhe, one of our academic subcommittee. And yeah, I hope you have learned interesting ideas and concepts about machine learning today for the first session. So after this, there will be a code along collab notebook so that you can understand like how the whole the various concept can fit into the big picture and your workflow. And at the moment, it is 7:40. I think we can take like around 5 minutes break. Yes. And if you have any question clarifying the slides, you can also raise the question. And we will be answering you immediately. Yeah, we're still here. We're still here. You can take a break. We will still be here. Google Colab. So I just reshared the Google Colab for those who are online and following us along. Yes, you may take a look first, and yep, we will be covering it soon after the break. So do you have people here physically, do you have any question? Any part that we might have, go through too fast? Yes? No? So I guess we we understand that because the content is quite, math heavy. So we also want to use a lot of visualizations and to help you understand the process, the concept. So I guess it might not have occurred to you, but I just want to emphasize the various aspects that we try to emphasize. So the idea, so let's say this slide, right? So you have the big X block. So X, as we have shared, is the input component of the data. So we color coded the row as blue and the column as red. So meaning that like from the X that is broken down to X1 and XD, it is broken down along the feature, not the data point. So that is like one color coded message. Another component is this training process, this whole, oh no, I should have opened up. Yes, another component is this training process, which we will go through again during the coding along. So we color coded the two output as, green. Are they different? Are they the same? Or what is the relationship between them? Oh, so the green. So the idea, right? The idea is that X is very high dimensional. You can see that like you have M data point and D attributes and features. So it is very high dimensional. So when you put this into the model, it comes out as thinner, less low dimension. So what came out is just one single vector of all the data point M by 1, M times 1 dimension. So M is because each data point will have its own corresponding prediction, right? So the green color that we're trying to convey is that the prediction and the label have the same dimension. Yes, so they are much smaller than X. And then we want to compare because the whole idea of supervised learning, what is supervised? Why do we call it supervised? We call it supervised because it's like something is, checking on our prediction, right? Supervised. I don't know why they come up with the supervised, but the idea is something is checking on the prediction that the model is making. And what is that checking? The label. The label is a ground truth. The label will be compared with the prediction in order to see whether the prediction is good or bad. And how do we know that the prediction is good or bad? It is by using the cost function. So during the presentation, we introduce you, okay, there is the linear, like y equals ax plus b equation. And then there is also a cost function. So how does it fit into the big picture? So the equation, the linear equation is by the ML model. And then the cost function is the comparison between the ground truth label and the prediction that is just made, right? So we have this cost. It's basically grading, right? Yeah, you take a test. So in your head, in your brain, that is your linear equation. Like you see the test, you try to write down your answer. And then the supervisor, the teacher come in with the cost function. Look at your transcript, not transcript. Look at your paper, look at your work and say, and check whether it is correct or not, right? So your model, the model is in the linear equation, the linear component, the sigmoid function reside within the model. And then the cost function is the grading function. So from that grading and cost function, we would try to improve, right? because the grade is the signal, right? If you understand your lecture, then the grade come out high. If you don't, the grade is low. So if you have low grades, it means that the teacher should pay more attention to you and try to teach you more or convey something else similar to that idea. So if the model predicts something that is very bad, the loss is very high. It means that, okay, the weight needs to change by a lot, like take larger step all the way until the loss is minimal, then the prediction is somewhat, correct. Yeah, so that is the idea. We use the cost function to adjust the weight, right? And that happened multiple times, right? It is not just, one, the teacher doesn't just teach you one day and then next day you can graduate from NTU. No. Throughout multiple weeks, they have to like feed you more information, try to make you better. Similar process. The line will start improve itself to align to best fit the model. And yeah, here you can see the error decreasing because the weight is changing in response to the loss function. So how does this gradient descent actually works? So it works by the idea of differentiation, right? If you recall, what is differentiation? It's dy over dx, right? Like when you do calculus, it's dy over dx. And what is the intuition behind that? It is the change, right? The ratio between the change, dy over dx. So the ratio between the change in y and the change in x. So intuitively, in English term, it means that how does the changing in the weight correspond to the change in the loss? And where should I change the weight to achieve the maximum improvement, right? And we avoid the math component here because in the next few workshop on deep learning, yes, deep learning, we will still go back to this concept and we will elaborate further. And I think it is also the general idea behind this one machine learning workshop as well. Definitely, machine learning is very vast. So if you go all the way, machine learning is just learning with data. And then there are many algorithms that you can use. Linear regression, logistic, decision tree, SVM, so on and so on. So why do we focus on these two? Because they are the most relevant to the deep learning that we will build upon in the next few workshops. And I will have more comparison at the very end when we finish the workshop, just to prepare yourself to the deep learning. Yes. And I think this one slide can also be confusing to some. Let's say the first line, hyperplane fitting. What is hyperplane? Hyperplane, I think, is just a shorthand to say, okay, let's go with the low dimension. Okay, so we all know that if we graph on a paper, it comes out as a 2D. And if we want to draw something straight on it, it comes out as a straight line. So now if we move one step further into the 3D dimension, now if we want to draw something to fit all the data point, right? We need a plane to try to encapsulate like as many points as possible, while the plane is still, it's still straight. It's still a linear equation. It is still straight. So if we go up to like 4D, 5D, 6D, how do we call that thing? It's not a plane because the plane is 2D. Therefore, the mathematician come up with a hyperplane. So the hyperplane can be whatever you want it to be, as long as it's linear and it is, in relative to the dimension that it exists. So yeah, so in a 3D environment, you will have a 2D plane. Yeah, 3D environment, you have 2D hyperplane. So it's just a dimension of the space minus 1. So it just trying to show the idea that the equation is trying to really fit the straight surface in a high dimension. And yeah, I think this is also the limit of what visualization can give you, because after this, you have to like intuitively understand that everything exists in high dimension. Yeah. So all these visualizations are just helping at the first stage. Yes. So MSE is mean square error. I believe that if you have been through like high school, there is also a practice, right? The line fitting practice, and mean square error is just the distance between the data point and your line. So that is why we use the MSE, trying to see if the line, the distance between the data point and the line, whether it is the minimum or not. So mean square error. Yeah, update, quick summary, logistic regression. Yes. So logistic regression is just linear regression, but on categorical task, right? Categorical classification task. It is just a very simple extension. Okay. So I think 5 minutes is up, and let's start with the runtime disconnect. Let's go. Let's start with the coding along session. So over here, you can see that first we import our libraries. First, we import our libraries because these are the libraries that you have been introduced in the earlier workshop. You have your Panda, which help us to use the data frame, tabular data frame, tabular data. NumPy is array manipulation. Matplotlib and Seaborn are just for visualization. So let's go back. I'm sorry. Let's go back to this. Okay, this right. So this training process gives you the relationship between your linear equation and the cost function. So yeah, so this is a kind of like a smaller scale version of training. So now we zoom in on a problem perspective. So yeah, we don't just in MLDA we don't just study MLDA because it is mathematical or intellectually stimulating. We also want to use machine learning on real life problem. So we have to define our problem, and we have to see if it is solvable in using machine learning. The problem should be reasonably defined, and there should be some reasonable relationship, right? For example, if you want to, let's say, predict the trajectory of the moon, well, Newton has already figured out the gravity and the equation, so probably using that is much better. What are the problem that is hard to use those analytical equation, like our friend Tianhe just shared, was the more high dimensional, the messy real world one, like spam filter. Okay, how do you write an equation to classify human writing, right? Those are the high dimensional one that requires machine learning. So first define your problem, then you acquire all your data. So before I continue on to describe the workflow, let's get you guys importing the data set for later on. So here in the Google Colab workspace, every time you open the Google Colab, it will refresh anew. So there's nothing remembered. Therefore, in the folder, there should be on your computer. There should be nothing. Right? There should be nothing. I also delete this to make sure. So first, the data preparation. We will be using two data sets, the housing and the diabetes data set from Kaggle. Let's go to Kaggle. Go to Kaggle. Right, data set. Oh, you see the black download button. Don't touch that. I think it gives you a zip file, which we don't really need. So go down to the data set section and download. Yeah, this small download. Diabetes download. Then next will be a simple drag and drop. So you open your thing, diabetes, housing, diabetes, drag and drop, housing, drag and drop. Okay. Diabetes in. Where's my housing? Housing. You're right. So now you have all the CSV file in the folder. Then you start running this line. Yeah, it's in. Right. So here the data acquisition is already done for you. Just download it. So now model setup and hypothesis. So what does hypothesis here means? It means that you have to propose various techniques to tackle your problem. The model, the thing that we are taught, right? The thing that we're teaching you right now, linear regression, logistic regression, those are one of the few techniques. As you can see, there are much more other techniques like deep learning. And if you have been following the deep learning news, there are like different models. You have DALL-E, you have Midjourney. So there is no single model or technique to solve everything. It is a constant try and error. So that's why we put the term hypothesis. It's like in science, right? In science, you hypothesize that something happened because of something else. Then you have to go out and test whether that hypothesis is true or not. Therefore, the model setup and the hypothesis, I lump them together. Then after that, we will fit the data into the model and evaluate it to see how it actually performs. Using various metrics to evaluate the model. If the requirements that we want is satisfied, then yeah, we use it in real life. If not, here we go again, right? New model, new hypothesis. Linear regression doesn't work. Let's try deep learning or multiple layers, right? So it is an iterative process. Okay, so let's jump right in. So first you have your data. House is equal true. Later you will know why I put this house equals true. The idea is that we are using the house data set. So when you do data equals import the data, read CSV, many of the function in the libraries that I will be sharing, you have encountered before. Or if it's new to you, then it is because it is all about experience and practices, right? What we are sharing is not exhaustive, but can be useful as a starting point. So when we first import, we notice that, okay, 500 rows and 13 columns. So based on the way that we visualize the data set, the rows are the different houses and the columns are the different attributes. So data describe is just a way to summarize what is in the different columns. So this is so here data describe, it only takes in the numerical column and it counts, it takes the mean, standard deviation, the minimum, the maximum. So it only gets you the information for the numerical column, numerical features, attributes. But it is very useful if in the more numerical heavy data set, right? But we don't want to discard the categorical. We want to use them as well. So how do we convert them here? So, you see that, okay, yes, no, it's like 1 and 0, triple E, computer, binary, simple, 1 and 0, correct? Then how do we do that? We can do that using this thing called label encoder from sklearn. So sklearn.preprocessing. So at this stage, we're still just pre-processing our data set in order for it to be useful in our model training. Data is not defined. What happened? What happened? Read data describe. Okay, yeah, data describe. All right, label encoder. right? So you import the label encoder, turn categorical into numerical. If you open up the label encoder, it gives you a lot of function, and you might be quite you're unsure like what method to use. For scikit-learn, the idea is quite simple. Like many of the function in scikit-learn have the same structure. So label encoder, right? You can call them as an operator, right? Operator. It do something. It should do something. But what does it do? So that the label encoder is kind of an operator. So inside the label encoder, usually there will be fit, there will be transform, there will be fit transform. So what does that mean? So label encoder is just a tool, and it needs to operate on something. And in this case, it needs to operate on the data. So label encoder you need to fit the data into the label encoder so that it knows that, okay, in this column, in this categorical column, there is a yes and there is a no. Then I will give out the corresponding numerical value, 1 and 0. So fit just mean, I fit my data in. What does transform mean? Transform mean, okay, now that I know that there are only two values, yes and no, I need to convert this yes and no into 1 and 0. So transform is that next step. Transform the data into the 1 and 0. And fit transform is just do everything in one go, right? So therefore, you can see that LE is the label encoder. Fit transform, the main row. So the main row on the right has the categorical data. And after the fit transform, it has the numerical data. And I overwrite it onto the main row. Right. So it's just like one line, but copy and paste, copy and paste. Why can I do all of this, like, just copy and paste? Because they are all like, yes and no, right? So the label encoder only need to convert yes and no. If they are different labels, like true or false, yes and no, yay or nay, it is probably safer to have, different variables like LE1, LE2, and operate separately. But here it's just yes and no. So I just lazy and copy and paste, right? So that is conversion of yes and no. So why is this conversion valid? It's because it is quite easy to separate the 0 from the 1, the yes from the no. It is like probability. You either do it or you don't. The problem arises is when we have more than 2 categories, 3. Let's say we have like cat, dogs, and chicken under the animal features. So how do we classify? How do we turn this into numerical value? We can use 0 for cat, 1 for dog, 2 for chicken. But that also that will carry the numerical baggages. You can say baggages. The implicit distance relationship between those numbers. So if dog is 1, so -1 is a cat and +1 is a chicken. So we are implicitly saying that, okay, the dog is 1 unit difference from a cat and a chicken. I mean, as a human, we don't even know like how much difference is a dog from a cat and from a chicken. But if we encode it that way, the computer see it that way, 1, 0, 2. That is like, the distance relationship. And for example, and a worst comparison is like, okay, the cat and chicken difference is 2 times the cat and dog difference. 2 divided by 1 is like 2 times. So there is a inherent risk when we classify when we turn category into number this way. And I think this is really relevant. The idea of distance relationship is very relevant, because if you recall, one of your cost function is MSE, mean square error, and mean square error is just calculating the distance between the data point and the line that you fit. So yes, in the cost function, it is trying to calculate the distance relationship. So now if you do the cat, dog, chicken, then it will use that distance to judge, to judge how well you fit the data. So that is very troublesome. 1 and 0 is not troublesome. 1 and 0, again, I emphasize, it is like on and off thing. You either do it or you don't. So if it's like 0.2, you can interpret it as, okay, it's not 0, but it is not likely to be 1 as either, right? There is still an easy way to separate them out. Therefore, what we have to do is using this concept of one-hot encoding. So one-hot encoding just means that, so cat, dog, chicken, so you have three, again, triple E, computer science, just use bit, cat, dog, chicken. Each of them are 1 bit, right? If you're a cat, then number 1 on the cat. So dog and chicken will be 0. So that is the idea of one-hot encoding. So how do we use the one-hot encoding? We use this one-hot encoding. One-hot encoding. So this is the PD get dummies data point. So which column we are dealing with here is the furnishing status. So the furnishing status give you furnished, semi-furnished, and unfurnished, right? So when we one-hot encoding, it gives us 3 columns. Furnishing status is furnished, furnishing status semi, furnishing status unfurnished. So yeah, so it's 100, 100, 010. So there are 3 bits, but there aren't 8 values. It's not 2 to the power of 3. It's just 3 different values. Like it's 1 at some of the location. You cannot have 2 ones, right? So yeah, so this turned the problem of having different categories into a yes and no question, a yes and no category. So this is how we convert the category to the numerical. You also see that, okay, include category equals true. Like, why do I have this random variable? Later, you will see. So now feature engineering and selection. Again, in our data set, not every data point is very necessary. We have to probe them if they are relevant or not, right? So here, FPLT figure is just setting up the figure. Setting up the figure. This is a matplotlib thing. I understand that it can be quite, you don't really know why, but it is a syntax, matplotlib thing. And down here is a Seaborn thing, right? Is one of the syntax. So bear with me, right? But the most important is this data dot call. So call here is the correlation. Correlation. So if you recall, your data is a data frame. Data is data type. Type of data is data frame. Is a data frame. So inside the data frame, it has the correlation function. So the moment you invoke the correlation function and you graph it out, it gives you this heat map of the correlation between the variables. How do you interpret this graph? So again, sorry, not again, I'm sorry, wrong word. You interpret it because it's a relationship between 2 variables. Price is 1 up here in the price because it is correlating with itself, right? If it's big, then of course it will be big. What we're interested in is the values of different pairs of variables. So areas and price is 0.54, meaning that the correlation is like 0.5. So if the price is high, it is likely that the area is also big, right? And you can see let's see what are the negative values. So price and unfurnished. So you kind of have that intuitive idea that, okay, if the landlord charging me very high for this room, for this building, probably it is, furnished, first class, very good. So the chance that it is unfurnished is inverse, it is in the opposite direction, minus 0.28. And the magnitude tell us what are the relevant information to use. Yeah. So But then let's use them more. Let's use them more. Let's make our life easier. So first, so here you can see the X and Y. So why do we use X and Y, like big X and Y? I would say it is a convention. Yeah, in machine learning, you can do other variables, no problem. It's just that in the machine learning convention, we use it. So if you are to use it in your work, when people read your code, they probably understand. So the first line is drop the price, drop price. Drop means, like remove price. Remove price, because the price is what we want to, is the label. Oh, again, not again. Shit, not again. What is our problem now? So we have this data. Our problem is to predict the price. Yes, our problem is to predict the price. So the price becomes our label, Y. You might think that, oh, I thought the Y is supposed to be at the back. No, that is just a positional thing. It depends on your problem to locate where the Y is. So price, in this case, is a Y. So therefore, we drop the Y and Y becomes the price. We drop the price and Y becomes the price. Yes, that is the idea that I want to say. So now we come to the idea of train test split. Train test split is to so the idea of the train test split, I want to use the analogy of students, right? Before our quiz, probably we have some mock quiz. So the teacher wants to give us mock quizzes so that we can train on it to make sure that we are ready. And then when the real quiz comes, you cannot, there's no answer key. So the idea of train test split in this machine learning case is similar. You split the train and the test. Train will be your mock test. Test is your real test. And usually we want to split that into, let's say, 80-20 or 70-30. In this case, we split that into 30% of the test, because we want to use this test as the way to evaluate, right? The real quiz is how the teacher will judge you. They don't care about your mock quiz. They assume that you learn from your mock quiz errors. So yeah, when we print out, the train is 380 and the test is 160. I think I have not run this at all. How about I just run all? Yeah, I'm too lazy. I'm sorry. Run all. Yeah, same thing. Yes. So now set up the model. So even though we introduced you to this a closed loop training model of predict, compare, calculate loss function, and update the model, we are still dealing with simple model. It's linear regression. It's linear, it's logistic regression. So the whole thing exists in these two lines, right? We import the linear in regression model. We initialize, and then we fit the data. Again, you can see the model.fit, like the encoder. Just fit the data. So this simple equation, right, handle all of the cost function calculation, the gradient descent, and the optimization that we just shared. So therefore, like, we take some liberty to move past the math, because really in using scikit-learn, it is just that. But point of warning, deep learning, we will dig deeper to the whole thing, right? So be on the lookout for deep learning. So after we fit the data, we predict. So we predict the train, we predict the test. So here I'm careful to put in the prediction, right? So that you differentiate between the two Y's. There is Y train and Y train prediction. Over here in the mathematical formulation, we put fx, but fx is quite troublesome, so we use Y again, but Y with prediction. So predict here is the output of the model. It's not the label. So now we have to compare it with the actual label, right? We have to compare it with the actual label. So here, the way we are visualizing it to have a feel of what is happening. So here we are graphing the predicted value and the true value. So the red line is the ideal. The red line is the ideal case. It means that if the true value is, let's say, 4,000, then the predicted value should also stay at the 4,000 point, which represent by all the possible cases as the red line. But not in this case. In this case, as you can see, 1.2 to the power of 10, 7. Can I drop the 10 to the power of 7? The correct data set, the correct data is 1.2, but our prediction is 0.7. So this point is kind of an outlier, right? Kind of an outlier. But again, individual point might not matter that much in our context because we are trying to build a model for many cases. So we have to look on the whole, whether the points are correctly clustered along this red line. So I would assume, okay, it kind of looks good. It looks good when the price of the houses is small. When the price of the house is high, it doesn't work that well. So what might be the problem here? You can say it's inequality, more people are middle class, so we have more middle class data. So it is predicting low prices better. And the rich people, there's only a few of them, so not enough data. That is a politics thing, but I think it is interesting to put in because again, even though we use scientific method and like engineering, it also should connect to the social thing as well. But this is the visual case. So on the left is the training set, the right is just the test set. So I think it is performing quite well, behaving along the linear line, along the expected optimal line. But how do we have a concrete measurement of whether it is good or bad, right? So here down here we import the mean square error, the matrix mean square error. And then we put in regression model, we put in the score, and we ask for the mean square error. So here there are two interesting things that I want to R square correlation, variance. I'm not sure if you have meet this, but this allows you to give out the, it allows us to judge whether it allows us to, how do I put this? It allows us to easily interpret the score. So the score, similar to the correlation, the score is between between -1 and 1. If it is nearer to 1, it means that there is a very high correlation. There is the model explain the data quite well. Oh wait, no, I'm sorry. This is variance. So it should go from 0 to 1, 0 to 1. I'm sorry. There's no opposite direction. So 0 is, it doesn't explain anything at all. 1 is, it explains everything. So the closer it is to 1, the better our model is. And because it is limited into 0 and 1, it is easier to interpret. Now, what is hard to interpret is the mean square error. You can see that it is like million, or no, billion, more than billions. So you might be wondering, what is happening? I thought mean square error, you want to minimize it. Shouldn't it be close to 0? So now the mean square error is dependent on the unit of the variable. It depends on the spread of the data or the numerical value of the data. So in this case, what is the label that we're handling? We are handling with price. Let's go all the way back up and check. Okay, the price starts around 1 million, 1.7 million and above, meaning that the value of the price is already very high. And now if we do mean square error, we square it some more, then that will be 10 to the power of 12. So that is the problem there. Even though we're trying to minimize the mean square error, the value come out can be very big. dependent on the variables that we are operating on. Yep. So, but because we are using linear regression, we know that this is the minimal mean square error that we can achieve. It's just that the explained variance R square is more meaningful, right? And you can see that train and test. So on the train data set is 0.7, but in the test set is 0.58. So it means that the model is performing very well on the training set, but it performed poorly on the test set. So it is that you are correct in all of your mock tests, but then when you go to test, it doesn't work. So that is why we have to split the train and the test, run through multiple times and to see the actual performance of the model. Yep. So now let's go all the way back up. Why do I put in the include category? Let's put false. So if we don't include the category, we don't include the main road, the guest room, we don't include the existence of the main road, guest room and stuff. We only take the numerical data, right? The numerical data like price, area, bedroom. So let's see how it performs. Let's see how it performs after we remove the category. If you recall just now, it was 0.7, right? So now the thing dropped to like 0.5 and 0.57. Okay, the test is still around 0.5, but the train is 0.54. So meaning that what variables you choose to put in the regression will affect the correlation. Will affect the performance of the model, right? Because when you are predicting the price of the house, probably it makes sense to include whether it has a basement, a main road, or amenities or other conveniences, right, as well. So that is why you have to convert the categorical to the numerical and try to include them as well. And yes, and again, you also need to use this correlation matrix to inform whether you actually choose it or not, right? So that will be the whole idea of linear regression. Yeah, linear regression. So down here is the matrix. See if it's good or not. So now we have two models, right? We have two models to compare. One with category and one without category. So which one performs better? I would choose the one with category. So this is the idea behind this loop over here. You set up a model, you train, you see how it performs, then you redo it again, like multiple times to see whether it works or doesn't work, right? The setup, evaluate, and that is what machine learning engineering do in real life, actually, right? In real life, you might think, oh, machine learning, probably they're making a lot of money, tons of money, but they come in, they try and error, right? Of course, they know a lot of different models, but at the end of the day, to tackle the company's problem, they have to do try and error. It is not an easy task. It's not an easy money glitch exploit. They have to put in the work as well, just like we have to put in the work to understand the concept. Yes. So now let's go to logistic regression. Okay, house equals false. Okay, let's put house equals true. Why do I want to put house equals true? Let's run all. I want to put house equals true here to graph area. Oh, I need to make this true. Okay, so these variables are just a way to allows me to use the same data set, but illustrate the various aspects of the whole training procedure. So I hope you don't mind that. So the idea, right? What I want to show is the housing data false. The housing data doesn't make sense in the case of logistic regression. So let's see. If I continue to use the housing data, house equals true. Let's say that I want to predict the pref area. So pref area, I assume, which is the preferable area, right? Whether this area in the house is preferable or not in the big picture. So therefore, I drop in the data set, I drop the pref area, and in the label, I put in the pref area. This is, I'm still using the housing data set. So again, see the correlation. The correlation is still the same, and I will still take everything. I'm sorry. I might not have demonstrate what is the value of, selecting the correct variables, but that is something that you can explore. I'm just breezing through right now. So X, we have all other components, and in the Y, you can see that it is the preferable area, whether the area is preferable or not preferable. So sklearn, yeah, import logistic regression down here. And similarly, train test split, 30%. I initialize the model. I fit in the data with one line, fit data, one line, very simple. And now when I want the prediction, again, model.predict. So does the prediction relevant? Is it relevant? Is it good? So I want to introduce the idea of confusion matrix. So we are still comparing between the true value and the predicted value. And what are the range, like what are the possible cases that it can go? It can be 0 or it can be a 1. So as you can see here, the matrix will give us a 2x2 matrix. On the horizontal axis, that will be the train. That will be the prediction, our prediction. If we predict it as 0, it will show up on the left. If we predict it as 1, it will show up on the right. If we on the horizontal axis, on the vertical axis, it will be the actual label. The 1 will be at the bottom, 0 will be at the top. So when we look at this, how do we interpret this? It means that our prediction never predict any preferable area. So 0, 0, 0 here are the count. How many times it predicts number 1. It doesn't predict anything. It just say, okay, all of the houses are bad, right? All of the houses are bad, 0. But in actuality, 91 of them are preferable. 290 are bad, actually bad. So this is not a good prediction. Similarly, on the test set, it is predicting something very bad. And I will touch on the idea of precision and recall later, but I just want to show you the idea that this data set is bad. The way it is working is very bad. And down here, later on, I will elaborate on this, but you can see that the curve, this curve that it is drawing is falling below the one line, right? It is curved in a bad way, in a concave. Concave is like eating in, right? Cave into something. So concave. Remember the shape. So why is it bad? Because this. So are we doing anything wrong here? Is the workflow correct? Yeah, I think the code is quite right. The problem is the problem statement. Right? The problem is the problem statement. What are we trying to do? Let's see if it makes sense, right? Let's see if it makes sense. We are trying to predict whether an area is preferable based on how many stories, how many room, how many guest room, basement, hot water. So it's like we are guessing whether the place is good, the area, right? The area is good, the neighborhood is good based on a single house, right? Maybe someone, like maybe a king pop into a jungle, build a castle. Wow, the castle is very good. But the jungle, who wants to be in the jungle? So that is the idea. Like, is there a true relationship is there a true and meaningful relationship that we can draw from this? So that is the problem of problem statement, right? We are trying to predict something that is impossible or might not have any correlation at all, right? Let's say if you want to predict if tomorrow rain or not based on my mood now, probably not, no correlation whatsoever. Bad. That is a bad prediction. So now that is why I put it into false. So I don't use the housing market, housing data set anymore. I will run after. right? So if it doesn't use the housing market, now it will use the diabetes data set. And the diabetes data set is predicting the outcome, whether the patient has diabetes or not. And you can see the various attributes. Do you have pregnant? Are you pregnant? What is your blood glucose, pressure, skin thickness? Do you have insulin injection? What's your BMI? What's your weight? Your age as well. So it makes sense, right? There are some correlation between these variables. There can be some meaningful thing that we can predict. If you see a person with a, not, you cannot see, but if you measure a person with a very high blood pressure, then probably the person might have diabetes. Diabetes is being fat. So fat, if you have a lot of fat, the fat will block your arteries, restrict your blood flow. So that is why you have high blood pressure. So it makes sense to, unwind it and say, if you have high blood pressure, we can predict your diabetes-ness. So it makes sense. Not that it makes sense, but the hunch is there. The hunch is there. The problem statement seems possible. Now let's build a model to see if it actually works or not. So if we graph it out, we will have the correlation as well. X and Y, logistic regression, metrics. Okay, now we have something interesting to judge or to make sense of. So similar to the linear regression, what we're interested in is how close is the prediction to the optimal case. So what are the optimal case? The optimal case also lies on a diagonal. If our prediction, now I think I need if our prediction predict number 1 and it turns out to be number 1, that is good. If our prediction is 0 and it turns out to be 0, that is good. So we want the diagonal line to be very big, just like how this heat map is also big because it is correlating with itself, right? So we also want, what we are predicting is correct. So if you see these two, the two numbers on the diagonal line is big, probably is very good. Of course, there will be outliers and cases that we miss out. But again, a hunch, if the diagonal number is big, that is good. That is good. Now, so just now, what I was trying to say is like a hunch, right? A hunch. Oh, it looks good. But what are the proper metrics that we need to look for? You cannot just predict people diabetes based on hunches. So now I want to direct you to this diagram. If you search for precision and recall and you open the Wikipedia, they will give you this. But it is also quite hard to discern, why is there a square, why is there a circle? So I want to separate out. On the left is how you separate out the prediction. So it will predict the circle as positive, and it will predict the non-circle area as negative, false. So red is wrong, green is correct. So that is the shape. So that is the prediction of the model. What is true in the real world is split left and right. So that is how you describe. So precision is you are taking the green circle over the whole thing. So when you look at the denominator, right? The denominator will inform you what is the space that the ratio is operating in. So the precision cares about the model positive prediction and how many of it is true, is correct, true positive. So that is the precision, precise. What is recall? Look at the denominator. The denominator is trying to look for the world, the true cases, the true cases. And it is asking how close is the prediction to the true cases, the world, the data true case. So one is judging whether it is good based on its own prediction, and one is assessing whether it is good based on the information in the world, right? So those are the P and R score. And when we look at this, we can see that the P and R score for 0 is like 0.8, 0.9, 0.7, 0.5, probably quite all right. Another metrics that is useful is the F score. So you can read up on the F score, but the idea is the F score try to encapsulate both the precision and the recall. It is not just a simple average. It has more to it, but you can see that the value is fall between the precision and recall. Support is just counting the number. So there are like 351 instance of 0, 186. So support, I think we can ignore. Now down to the accuracy. I think the easier way to look at is just the macro average, right? The macro average. So the accuracy is like 0.78, and down here is also say 0.78. But again, we cannot just rely on the accuracy alone. What does the accuracy tell you? The accuracy just tell you whether your prediction is correct or not, right? But it doesn't give you any differentiating factor between the positive and the negative. Why might this be useful? Why might this be important? Because we are predicting diabetes, and in the medical field, we want to save lives, right? We want to save lives. So if we predict a disease wrongly, it will cost life. So maybe we would want it to, okay, sometimes I will over prediction, right? I predict that you have cancer, so you should go for additional treatment. But turns out you don't have cancer, but it's okay, like you're still fine. If we misdiagnose a real person with cancer, that is bad, because if we predict it wrong, then that is bad for that person. So accuracy is just whether you predict any case correct or wrong. But with precision and recall, you can see that what we're interested in is the true positive, the green half of the circle. So the true positive is the thing that we're interested in. So diabetes, we want to target the diabetes people, as in we want to figure them out so that we can cure them better, right? We want to figure them out so that we can cure them better. It is okay if we overshoot a bit and diagnose many people, but those people will be also under our care. And that is good. We want that. We don't want to left out anyone who has diabetes, but we didn't catch. Yeah. So depends on the industry, depends on your application. These metrics will be very important. So yeah, there are various metrics that you can have. So how do you invoke this? Classification report and accuracy score. Okay, so now we go to the receiver operating curve, ROC, and area under the curve, AUC. So the prediction that we have above here, right? I also comment it out. Prediction, the assumption of the threshold is 0.5. So just now when we do logistic regression, Tianhe also shared that different classes, there will be a 0 to 1% probability of being in that class. So if we invoke predict, which is 0.5, so if your probability is 0.4, it will say, okay, that is not in this class. If it's 0.6, oh, I accept you to in the class. So if we use predict, it will just be 0.5. But a better method to evaluate whether the model is good or bad is to use this operating curve. So how does this operating curve works? It works by first, instead of getting the threshold, instead of getting the 0.5 threshold label, we would want to get the probability instead. So if it turns out to be 0.4, we want 0.4. We don't want it to snap back to like, okay, because 0.4, it becomes 0. We don't want 0.4 become 0. We want 0.4 to stay there, because the probability is useful. The raw probability is very useful. And how do we use that? So I want to direct you to this curve again. Not again. No, I'm sorry. Wrong words. So true positive and false positive. again, okay, again is the same idea. Like sometimes we value the true positive more than the false positive, and like vice versa. Okay, how do I explain this? Let's direct our attention to the right on the S-shaped curve first. So this S-shaped curve, if you recall, right, this is the result of the sigmoid function. This is the result of the sigmoid function. So every value that span from minus negative infinity to positive infinity will be squeezed into 0 and 1, like, and it will form this shape, right? And what we want is the green circle. The green circle is like the true positive. The green circle is the class that we want. Cross is bad. Okay, let's go with green is good. Cross is bad. Let's go with that. Green is good. Cross is bad. So so in our world, it is very messy. Not a single features can help us clearly classify anything. And even with multivariate linear regression or multivariate logistic regression, there will be some like fuzzy like in the middle. So for example, just now, like I said, right, let's say feature X is the blood pressure, high blood pressure. So if I just say that, okay, people with high blood pressure probably has the diabetes. But you can see down here, like a person with diabetes with very low blood pressure, what might be the case? Well, people have different genetics, people have different living environment. Yeah, so that is the messiness of life. So you can see the X and the 0 kind of like mix and match together in the middle. Very hard to discern. So the problem now is, where do we put the threshold? So the threshold is denoted by the orange line. Yep. Earlier, the threshold is assumed to be 0.5. But we don't want to just straight out define 0.5. We want it somewhere. But where that might be? Where is the good threshold? So the way that the ROC curve is drawn, it just skim through the whole thing. Like, let's define the threshold from 0 all the way to 1, right? So as you can see, I draw 3 representative line, TH threshold 1, 1, 2, 3, and it will correspond roughly. It is not the same thing, but roughly there, just for illustrative purpose, so that later on, if you encounter this curve, you know how to interpret it. So threshold 1 will be up here. So if we draw the threshold down here, it will be along this way. Okay, as we go up, the probability, as we define the threshold as going up the probability, we are traversing along this orange curve, right? So if threshold is down here, TH1 is down here, then TH1 is somewhere up here. So TH2, TH3 down here, right? As we traverse this, it goes down. And on the axis, you can see false positive and true positive. This goes back to the idea of whether we are, catching the correct positive or not. So what does true positive mean? True positive is O being above the threshold. So if all the O's are above this TH1 threshold, our true positive rate is very high, right? So because it is a rate, what is it? What is the denominator? Denominator is the prediction. Yeah. So if it is a good thing, if it's diabetes and we manage to get it above the threshold out of the whole prediction, then it will have a high positive rate. So you see, like the threshold down here, all the O's are up here, so it has very high positive rate. And in the limiting case, right? The limiting case, when the threshold is like 0, when the threshold is 0, it means that all the O's are above. So yeah, when the threshold is 0, or we have very high positive rate. But the negative side of high positive rate is that we are misclassifying the X, right? We are misclassifying the X. We are saying that the X is supposed to be O, but they're not O. So again, going back to our medical example, it is true that we want to detect as many diabetes people to treat as possible. But now if we go out to the world and say, okay, everyone go to diabetes treatment, even though it's a newborn child, even though the person is very healthy, exercise every day, that will not be a good social policy, right? So being very high for true positive doesn't make sense at all. So therefore, we should move along this line. So we want to reduce the false positive. Yeah, false positive is X being above the threshold. So if the threshold, let's say threshold 0 is down here, then all the data point will be above. Yes. So at this point, the true positive is high and the false positive is also high. The inverse is also true. If we put the threshold all the way up to number 1, then we fail. Then we fail to catch the true positive. Even though we minimize the false positive, right? We fail to catch the true positive. So what is the best, again, optimal case? What will be the best model? The best model would be up here. We have perfect true positive and no false positive at all. So we don't detect wrong cases. And we always, every time we detect a patient, the patient turns out to be unwell and we can treat it on the spot. That is good. But it is not a real thing, right? It is hypothetical, it's aspirational. But we cannot achieve that. But the idea is there is a trend, right? If our model lean towards that point, up top left, it is good, it's generally good. And if our model is going the other direction, it is bad. So in this case, yeah, it is curving up, which is good. If you recall just now, the housing price, the housing preferable area, it was curving down. It was curving down, which is bad because it doesn't have any strong predictive value. Yeah, so this is how you describe the receiver operating curve and area. Okay, area under the curve. Area under the curve is just trying to say what the blue arrow is trying to say. If the curve is curving upwards to the left, then the area under the curve is large. If it is curving down here, then the area under the curve is small. So basically, yeah, instead of drawing arrows, they just, calculate the area. That makes more sense or easier, simpler. And all this code is just to draw out the lines. Yeah, draw out the line. And I hope you might pick out some very common common usage like plot, X label, Y label. Because if you go on to do machine learning or even Python, you want to plot something, you will deal with matplotlib. So I don't expect you to know all of these at the moment, but it's good to keep them in mind and save them somewhere because you will be seeing them a lot more. And so the threshold, so this threshold is just printing out where are the different spots along the line, right? So 0, so where are the different spots along this line? And that will be it for this regression. So how do we evaluate a regression model? Is based on this operating curve, whether it's curve upward or not. If there is a model that allows the prediction to curve all the way up nearer to the corner, then it will be better than this one. So this curve doesn't tell us where to put the threshold, right? It doesn't tell us where to put the threshold. It just scans through all the threshold to see whether, as on average, like as a whole, whether the model is good or not. It doesn't tell us where to put the threshold. But of course, it also depends on what do we want to do. Do we want to catch all the, sorry, not catch, but do we want to cure all the diabetes? Or do we want to make it a burden for everyone to visit the doctor, right? So we can put it up here because we want high true positive, or we want to put it down here because we don't want to bother everyone to go to the hospital every day to check for diabetes. Yeah. And okay, so in this case, it is still 0 and X. Okay. First of all, the whole notebook is done. I think I have delivered everything. Now is the interesting and fun fact notes that will help you along the journey. And to express, there are still things to be learned. So in this case, what is our category? What is the thing that we are trying to classify? It is whether the person has diabetes or not. So yes or no, truth and false. So it's still two classes. But there will be times where we would need multiple classes. We want to differentiate, right? Your machine learning models, when you use, let's say, computer vision, you want to classify table, chairs, people, cup. So it will be much more complex than this. But the idea is, but luckily, the idea is everything is still contained in this training process that I just shared with you. So even though we only have one workshop on machine learning, this one workshop in machine learning is specifically for supervised learning, encapsulate the whole workflow of deep learning in the future as well. The problem is just that, because it is still in block diagram, it is still very high level. We have not touched the complex math, but the idea is that the big picture is already complete. You have your input, you have your prediction, you compare using the cost function, and you use that to update. So in the case that I raised just now, so here we have binary cost entropy. So it is two label, 0 or 1, right? What the cost function is doing is that if the label is 1, you had, if you predict 0, you have higher cost. If you predict 1, that's good, low cost. But there are only 2, 0 and 1. If we have multiple classes, then this whole cost function will be altered severely, yes, drastically. And today we have not touched that, but bear in mind that it will be more complex. But the principle is the same. The principle is the same in a sense that we would want to increase the cost for a wrong prediction. So in the case of classification, there is no distance measurement. It's not about distance. It's about whether you get the correct classification or not. So that is something to warn you in the future that more interesting thing will be coming if you pursue down the machine learning path. So closing remark is that will be the end of machine learning workshop. Yes, I hope you enjoy the process. And even though machine learning is very big and wide, and it is even the bigger set, right? If you draw a Venn diagram, deep learning is the subset of machine learning. So technically, there is much more to be said about machine learning. But because we want at the end of this series for you to catch up with the latest, trend and technology. And the latest trend and technologies right now is deep learning and all the computer vision and natural language processing. So we kind of skip over the traditional machine learning stuff. We go straight to deep learning. So in the future, in the next few workshops, we will be tackling deep learning. But the good thing is, even though linear regression and logistic regression are very simple, they are the foundation of the deep learning deep learning workshop in the future. So you have seen the linear equation. You have seen your matrix multiplication. I steal a slide from Tianhe in the above. Okay, so this is the node, right? This is the node of a neural network. So you see this chunk on the left, that is basically your linear function, your linear equation. Then the sigmoid is called an activation function, right? The activation function wants to inject non-linearity. Yeah, the left is linear, the right is non-linear. Then pass the signal on to the next step. So in linear regression, we just stop at one node. But in deep, why is it called deep? Because we have multiple nodes all the way along the pipeline. So that is why. So linear equation, matrix multiplication, very relevant. Cost function, the same. We still need something to judge, as in we still need something to compare whether our prediction is good or bad. That will still be relevant in deep learning. Gradient descent is like the core idea of updating deep learning. Let's a bit maybe talk a bit only a bit only, right? Differentiation, right? When we do calculus, the way we differentiate is we look up the table, right? Dy dx, what is the equation, sine equal convert into cosine. So that is analytical. There is a lookup table for you to refer to. But in the real machine learning world, many of the functions can be very complex and you cannot differentiate it that way. So there are other techniques to differentiate. And then there are other techniques for you to descend the gradient. So same concept, different implementation. Gradient descent still very important. And activation function, yeah, sigmoid can be called as an activation function, but there will be more activation function to be used. And yeah, linear regression, logistic regression, quick and fast, and call it, call fit, call predict. And the deep learning workshop will go through the training process. So as you can see, we skip out this part. We skip out how do we get from input to output? How do we get to update using the gradient descent? But in the deep learning workshop, we will cover that as well, the whole training loop. Yes, and that will be it. Wow, yeah, that's great. Then now I would like to thank you for participating, and I would like to invite you to drop us a feedback. And for those who don't know, it is a part of machine learning MLDA LEARNOVA series. So we want to reward the members who stay with us all the way, and we want them to truly learn something. So they are there is a quiz that they have to go through to reinforce their knowledge. But if you are an SCSE student, right, you just know about us through the recent email, you are encouraged to do the quiz as well. But it will not be recorded. It will not affect you in any way. But for you, what we would want is maybe the feedback so that we can improve. For the quiz, it is for the LEARNOVA member. And all of this will be put up on our MLDA handbook. And I understand that many of the SCSE students, they join us through the Telegram official channel. And I think we have not shared the handbook there. We will be doing so very soon. So thank you. Thank you and have a good week. Have a good week. Have a good day. And yes, do you have any question? Do you have any question? Yes, that is the important question. Do you have any question? Do you have any question, physical people? All right. I hope you learn a lot. I hope you learn the linear thing. And see you in the upcoming workshop. Okay, actually, yeah, I ask you to, I know that the physical participation is dropping, and because it's the later half of the semester. Oh, I should stop the share. Oh no, I shared the quiz. Oh, it's okay, it's okay. If they follow the recordings, they deserve the feedback. Then you know we will take into account next time. Sorry. Yeah. Oh yes, I hope, yeah, after you're all done and you're ready to leave, then we can have like a group photo. So yeah, end of the workshop. Yeah, thank you very much. Uh, Earlier I was saying, yeah, the participation is dropping. Uh, but I still encourage you to come physically, because if you really need help and uh have any question, really, like we really want your question, because we believe that we have uh tips and tricks that we want to share, but we might not know what, because no one asked question, right? So I do hope you continue to support and participate. Go to the physical and, yeah, engage with our subcommittee to hear the juicy tips and tricks. Yes. Huh? Oh, what? Oh,